Chemical reactions are all around us, but have you ever stopped to think about how we know how much substances need to go in fireworks to make them work correctly? Or even in an airbag, how do they know how much of each substance is needed in the airbag so that it inflates to the right amount and isn't too dangerous by not inflating enough or inflating too much and causing more harm? Well, the answer to this is a balanced chemical equation and the law of conservation of matter.
You've seen balanced chemical equations before, but maybe never stopped to really look at what you can learn from an equation. For instance, the three reactions that are coming up on your screen right now help demonstrate the law of conservation of matter by showing that the elements that are reacted on the left side are also produced in the products on the right side of the equation. The large numbers that are in front of each item tell you how much of each element you have, and you'll notice that both sides match up, which is why we're balancing the chemical equation, is so that we show that matter cannot be created nor destroyed. Right now would be a good time to pause your video and write down these vocabulary terms in your notebook. One of the objectives of this video is that by the end, you should be able to create your own definitions for each one of these words based off what you've learned in the video. The other objectives are that you can mathematically represent a balanced chemical equation by adding the correct coefficients and using a particle diagram or balance beam diagram to show the amount of particles on both sides.
To put into practice balancing chemical equations, we're going to look at a reaction that we have done several times in class, including every time that you light a Bunsen burner. So you're going to want to write this reaction in your notes. CH4, which is methane, plus oxygen gas, O2, will react to produce the two products, carbon dioxide, CO2, plus water, H2O. If you need to pause the video to make sure you have this reaction written out, please do so. As we watch the video, we may remember that methane was in liquid form inside that test tube. And as heat from normal room temperature water was added, more methane vaporized into a gas and reacted with the oxygen in the room and burning, just the same as every time we light a Bunsen burner. We now take this into practice and balance this equation by using the coefficients to make sure that both sides have the same amount of particles.
To represent the reaction that we saw in the video, we're going to use the PhET simulation. The PhET simulation provides us a couple of visual representations to help understand why we balance equations and what's actually taking place in a balanced chemical equation. Across the top, you see the little teeter-totters. And the teeter-totters are going to show you if the reactants on the left side and the products on the right side match up. In these boxes, these will be the particles for the particle diagrams, and you'll be able to visually see if both sides match up. Then across the bottom, we have our traditional equation that we use to balance equations. In front, you notice there's these spaces to put in the coefficients. Remember, your coefficients are the numbers that represent how many of each particle are needed to make the reaction take place. So to do that, we have to make sure we at least had a reactant of methane and that we at least had a reactant of oxygen available for this reaction to start. Notice what happens when we do so. It shows us that on the left side, or the reactant side, we have one particle of the carbon, 4 hydrogen, and 2 oxygen. Now, because we cannot create nor destroy matter, the law of conservation of matter, or mass, remember that you have to have the products have those particles represented. So what we're going to do is we're going to check and make sure that both sides are balancing and matching up. So let's start with the carbon. We notice that we have one carbon on the reactant side and one on the product side. Take a look at your particle diagram. The carbon's represented by the gray particle. There's one here and there's one here. The coefficients tell us that we have one carbon and one carbon. So far our carbon's good and matches up. Let's move on to the hydrogen. So according to our little balance beam, there's 4 hydrogen on the reactant side. So we come over here and we see the 4 hydrogen around the methane. The little white dots represent the hydrogen. On the product side, we have 2 hydrogen. The little white dots are 2. It's not going to work. We have to have the same amount on both sides. So we're going to change our coefficient to 2 waters. The 2 waters give us 4 hydrogen. Notice our hydrogen is now balanced. In balancing equations, you'll tend to fix something and it's going to break something else. So as soon as we fixed this water and fixed our hydrogen, notice my oxygen went up to 4. On the reactant side, there's only 2. So we're going to come back over to the reactant side and add another one. The PhET simulation tells us we did it right. Let's look and see what we did again. We had 1 methane, which gave us 1 carbon, 1 carbon dioxide, which gave us 1 carbon. We had 4 hydrogen on the reactant side, so we came over here and put 2 waters to give ourselves 4 hydrogen. That gives us 1, 2, 3, and 4 oxygen on the product side, meaning there had to be 4 oxygen on the reactant side. We did that by creating 2 oxygen. Our balanced chemical equation is 1, 2, 1, 2. All right, this next reaction you're going to try to balance on your own. So before you do that, let's talk about what I want you to do. In your notes, I would like you to write down this equation. Nitrogen, N2, plus hydrogen, H2, produces ammonia, which is NH3. This process is called the Haber process when we react nitrogen and hydrogen gas to produce ammonia gas. So once this has been written in your notes, you are going to try to balance this equation. And I also want you to pick one of these 2 tools, whether it be the balance beam or the particle diagrams, to show that what you wrote for coefficients actually balances both sides of the equation. So go ahead and pause the video, attempt to balance it, and then when you're done, resume the video. Hopefully you had some success balancing this equation, so I'm going to do it really quickly here and show you how I went about doing it. So first of all, I have to have at least 1 of each particle on the reactant side, and I have to have at least 1 particle on the product side. Because remember, we cannot create nor destroy matter, so all the particles have to be accounted for. In this reaction, nitrogen's a diatom, so it starts off as 2. If we look down here, the coefficient of 1 tells us we only have 1 diatom, so 2 nitrogen on the reactant side. Product side, I only got 1 blue nitrogen, so I'm going to go ahead and add another one to balance it out. Notice the 2 blue match up to the 2 blue on the reactant side, and my balance beam matches. Remember, as I told you before, you tend to fix something and break something else. You fixed the nitrogen, you broke the hydrogen. Now on the product side, we have 6 hydrogen, because we have 3 on this ammonia and 3 on this one. We come back, and hydrogen being a diatom, we're going to need to add 2 more, or 3 total hydrogen. As we do that, we notice everything's balanced. My coefficients for this equation are 1 N2 plus 3 H2 produces 2 NH3. This final is your individual practice. You'll balance these equations on your own and provide a visual representation of each equation to show that you've actually balanced it correctly and that all the particles are present, thus demonstrating the law of conservation of matter. If you have any questions, please make sure that you bring those with you tomorrow to class, and we will answer them then. Thank you.